All right, good afternoon, everyone. Good afternoon. Okay, so today we're going to spend time studying the last type of a fundamental function response, and this is called as the impulse function response. Okay. Impulse response for first order systems, but before that we need to define what is meant by an impulse function. Impulse function is also sometimes called the Dirac delta function. And in reality, this is not an actual function, it's more of a distribution, but we will not get into the aspects of a difference between a function and a distribution. We will still call it as a function. It has some very different types of properties, okay, as you're going to see. So I'm going to define what is meant by a unit impulse function, and then we will come up with a way of actually deriving this graphically, okay, not mathematically, graphically. So unit impulse function is called delta of t, the Greek letter delta, okay. And mathematically it is defined as follows. So delta of t, this is equal to 0 when t is not equal to 0, and it has a value of infinity or undefined value when t is equal to 0. So typically undefined versus infinity, we will call it as infinity, okay. So it has a magnitude of infinity when t is equal to 0. So this is a discontinuous function. There is a discontinuity taking place or a singularity taking place at t is equal to 0. Everywhere else, this function has a value of 0. Okay, that's the first definition. The second thing that we will look at, and this is something that will spill out as we do the derivation of this function, is integral minus infinity to plus infinity, the limits being on time, delta of t, dt is equal to 1. So very interesting function. It has a magnitude of infinity at t is equal to 0. But if I take an integral of this function from minus infinity to plus infinity, which means I'm considering the area under the function, the area under the function is equal to 1. Very weird. Okay. So what gives? And how does this function have this particular form? We will start looking at that. Yes.
So it's saying that it's infinity as time is equal to zero. So I'm like thinking about impulses like that. Boom, right? Technically, your fist is on the ground for like more than that amount of time. So like, are there impulses that's greater than just an instantaneous moment in time?
We're getting there. We're getting there. Okay. All right. So to get to where you're talking about, or where we want these definitions to make some sense, physical sense, let me start with the function. Okay, so how? So start with the following function. I'm just going to define it. Okay, so this is having a value of 0 when time is less than 0. Then it has a value of t divided by some time capital T. Okay, little t is the variable time, capital T is a value of the variable. Okay, this is between 0 and t, and then it has a value of 1 for t greater than some t. So what is capital T? It could be 2 seconds. What is capital T? It could be 0.5 seconds. Little t is the variable. Okay. So let's start off with this function. Let me sketch this function. Little t f of t. Okay. It has a magnitude of 1. Let's say this is 0. This is capital T, 3 seconds, 5 seconds, 0.2 nanoseconds, does not really matter. Okay, so let's say that is capital T. When time is greater than capital T, the magnitude of this guy is equal to 1. So let's mark 1 here. Right? The magnitude is equal to 1. Between 0 and capital T, what does this function do? Could anybody tell me? Between 0 and capital T, what could this function be doing? Look at the definition of the function. Yes. It's a linear increase, it's a ramp. Right? Because it's 0 at t is equal to 0. And when t is equal to capital T, it's equal to 1. And in between, it is raising linearly. Okay? And so the slope of this function, you could consider it from the interval 0 to t and 0 to 1. So the slope is going to be 1 by t. Does this make sense to everybody? Okay? So we start off with this function. So start with this function. Then my next step is, I'm going to take this function and I'm going to differentiate it. I'll call that as a new function g of t. I'm going to differentiate this function. So this is df of t by dt. Very non-rigorously, I just go inside the function f of t and differentiate each of these terms. Differentiation of time for 0 is 0, so it is 0 when t is less than 0. What is the differentiation of little t divided by capital T? It is just 1 by t. Okay? So this is 1 by t when I am in this particular interval. And what happens after that? Differentiation of 1 is 0, so it is 0 when t is greater than t. I want to see if this makes sense to you. I just took that function, differentiated. Nothing funny going on here. No tricks. Okay? I want to plot this guy. So let's plot g of t. This is t. This is g of t. Okay, start at 0. This is capital T. Between 0 and capital T, what is the magnitude of this function? It is equal to 1 by t. Stays the same. And right after t becomes greater than capital T, has a value of 0. Right? This function is called as a rectangular pulse. If you look at this kind of a function, do you see anything that could be its characteristic trait, characteristic hallmark? Looks like a rectangle, fine. When you see a rectangle, what are the things you can do? You can probably, yes?
Wouldn't T be the only thing that changes it? So it would like make it change the dimensions of it?
That's one thing, absolutely right. If I change the magnitude of T, this will either get squished or it will get enlarged, right? That's where we are heading to. Now, if you think of rectangles, you think of areas, yes?
The area is the same.
The area is the same, okay?
Area is 1.
Area is 1. Okay, so the area is equal to 1. This is an interesting function, right? Things are getting interesting. Now here is what I'm going to do. I'm going to do two things. First thing is, I'm going to take the function f of t, okay, and maybe I can sketch that here. F of t. I had my initial function start off in this manner. So this was 0, capital T. This was f of t, and this was equal to 1. Can you tell me what will happen if I say that capital T is reducing? So let's say that in this figure that I've drawn here, capital T was 3 seconds. Now let's say that capital T became 1.5 seconds. What would happen to this figure? Yes?
It would just shrink.
It will shrink. As it shrinks, what happens to the slope of this line here?
It goes straight up and down, essentially.
The slope of the line keeps increasing. As I reduce capital T, the slope of this line keeps increasing. You see, if T was 3 seconds and then I said, okay, make T 2 seconds, slope would be steeper. Slope would be steeper. Slope would be steeper when I say that T tends to 0. What will I get? When T becomes equal to 0, what will I get? I will have a line, yes? I get a step function here. Because the slope is infinite, but the magnitude is 1 all the way after T is greater than 0. So as limit T tends to 0, f of t gives me a function u of t, which is your unit step function. FCN is function. Okay, so this is the birthplace of the unit step function. This is how it is born. And you can sketch that here. This is t. This is u of t. And this is drawn as follows. This is 1. This is 0. Everybody with me so far? I started off with some generic function f of t. I just pulled that out of thin air. Bear me on that. Then I have this f of t. I took the derivative of this. Quite non-rigorous, I would say. But at least its derivative exists in the classical sense. So I can have a function that I've drawn there, which is g of t. Okay? So I have g of t. I have f of t. I then say, okay, take the limit of t tending to 0. What happens to f of t? It becomes a unit step function. I do the same thing for the derivative. what happens? Take a look at it. Capital T, 1 by t. This was g of t when t is 3 seconds or 5 seconds. Then I say, okay, as time reduces, what's going to happen to this? It's going to start becoming a little shrinked in the x direction, but it will also equally grow in the y direction. Because I have to keep something constant, right? I have to keep the magnitude of the area to be equal to 1 at all times. So no matter what happens, as t tends to 0, this is going to keep on having an area of 1, but the magnitude is going to keep increasing. So I'm going to see that this is going to rise up a little more. And this is the limit of t tends to 0. And so what happens when t is actually equal to 0? Yes? It becomes the impulse function. Fantastic. And that's how the impulse function is born. Okay, so in this case, this becomes delta of t. And please notice how this is written, okay, how this is drawn. This is t. Delta of t is the unit impulse function. When you draw the unit impulse function, here is what you do. On the y-axis, you put a magnitude of 1. What does that magnitude represent? That magnitude represents the area under the impulse function. It does not represent the magnitude of the impulse function itself. Okay? This is the area under the impulse function. So this 1 here. It is not the magnitude of delta of t. The magnitude of delta of t is infinite, or if you want to be really more rigorous, it is undefined. It's infinitely large, so you can't define it. Does this make sense to everybody? Question?
Does the arrow with the line blocking it represent the area, like just?
Yeah, just the number 1 represents the area. And I'm going to show you, okay, this could be equal to 1, or if I multiply this by some number, that would change, and that would become that number, the magnitude of that number, because the area would then be changed. I'm either increasing or decreasing the area. Okay. So keeping all this in mind, so you have these 4 plots. This is figure 1, then you had figure 2 f of t, then you had figure 3 and figure 4. I want to write down the equations that we have obtained. Okay. So for today, I'll just move this up because I need to see this. Well, I guess I can't. So it's stuck there for eternity. I want to make sure everybody has all these taken. Okay. All right. I'm going to draw these 4 plots once again, just for my own sake. You don't need to. Okay. So figure 1, 2, 3, and 4, all in the same panel. Time. Okay. First figure is f of t. And we know this is a ramp until capital T. Has a magnitude of 1 as I pass capital T. Okay. Then the second figure is g of t, which is df by dt. Okay, if I draw this is a rectangular pulse. This is 1 by t, and this area is equal to 1. This is figure 1. I'm going to call this figure 3 because I have figure 2 coming up next, which is this guy, and then figure 4. Figure 3 is a unit step. How do I get the unit step? By taking f of t and setting the limit to 0. Okay, so I have u of t. This is the limit t tending to 0, f of t is equal to 1. Fourth figure is the impulse. Delta of t is limit t tending to 0, g of t. This is equal to 1. The 1 represents the area under this curve. Okay, the 1 is the its magnitude at t is equal to 0 is infinite. This is 0, 0, 0. What I want to get at is, okay, what are the fundamental mathematical relations between these two or these three or these four characters? And look at this. Started f of t and started g of t. So from figures 1 and 3, I have g of t is it's a first relationship. Second relationship that I have is a limit t tending to 0. F of t gives me the unit step function u of t. Okay, once again, I'm just rewriting stuff from there, but you'll see where I'm going with this. Then limit t tending to 0. G of t gives me delta of t being the unit impulse function. Okay, u of t is the unit step function. Here is what I'm going to do. Take a look at that last creature. This is no surprises there because g of t is defined to be df by dt. Okay. Start with f of t, take the derivative, get g of t. Take g of t, set capital T to be going to 0, you get the impulse function. Take f of t, set capital T to be 0, or you in the limit of that, you get the unit step function. Here is what I'm going to do. This differentiation and the limit can be switched. Why is that? Is because the limit is not with respect to little t, it is with respect to capital T. Okay, so I can switch the limits. Okay, so I can do this. And do you see the next logical substitution that comes through? What is that? That's u of t. So the derivative of the step function is actually the impulse function. We had previously seen that the derivative of the ramp function was the step function. Okay, lecture 16. This is now a different kind of result, so I'm going to substitute u of t. So fundamental result. Does this make physical sense? It makes complete physical sense because what is the value of u of t? As time is less than 0, it is 0. So its derivative is 0. What is the value of u of t after time is equal to or greater than 0? The derivative is 0 because the value is 1. What is the slope of the function u of t at t is equal to 0? Infinite. Which makes absolute sense because the step function derivative is the impulse function, and so the magnitude of the impulse function when t is equal to 0 is infinitely large. Okay, so from a physical perspective it makes sense. From a mathematical perspective it seems like sleight of hand, but you can follow the thought process here. Okay, and this ends up having the following value. And I want to see if everybody is on the same page. This was one result that I had. The other result, recall from before, dr of t by dt is u of t, where u of t is the unit step function. And r of t is the unit ramp function. FCN is my shorthand for function. And of course, this is the point that we want to make. One of you mentioned at the beginning of class that an impulse is something like I hammered the table, right? That's an example of an impulse. I broke my watch the last time I did it last semester, or there's a year before. So I'll make sure it's my life's gift too. So you apply a hammer blow on a body. That's an example of an impulse, right? Why is it called an impulse? Theoretically, its magnitude is not infinite, but you can think of it as having a very, very large magnitude applied over a very short duration of time. That's an impulse, okay? This is a mathematical definition of a function whose magnitude is infinity. We cannot have it in reality, physically speaking, but I can approximate many phenomena that way. I can take a football, I can kick it. I'm imparting an impulse to the football. I'm having a very large force applied on it for a very short duration of time. And so many physical phenomena can be modeled in terms of the impulse function, okay? For example, you do shock loading of bodies, right? Something comes, there is an impact testing of bodies taking place. When you're doing, if you're designing cars and so on, impact testing is really, really important to understand the crashworthiness of the structure, right? So impact loading is an example of an impulse loading. Okay? So I can make use of practical phenomena, and I can say, okay, hey, this looks suspiciously close to an impulse function, and I can now approximate that forcing by means of an impulse function, and then approximate the system itself as a first order or a second order system, and I can obtain the solution for the system. Okay? So this is where we are heading towards. I want to see if there are any questions so far. Sounds like mathematics, but it is very, very practical, very applicable. And there is an even more deeper meaning. I want to maybe talk about that before I go next. So here is a more deeper meaning of the impulse response. Take an arbitrary function. Some h of t. Some arbitrary function. I can do the following approximation on this function. I can take this function and I can approximate it as a series of so on and so forth. You see, I can approximate it as a series of rectangles, right? Because the area under the function is the same as the area of all of these rectangles put together. Now, each rectangle is a pulse. So if I know how the system responds to one of these, which is what we are going to achieve today, then the powerful thing is I can find out the response of the system to any arbitrary force applied by just summing up the responses of all of these pulses put together. This is something that you do in vibration analysis, and this is called as the convolution integral approach. I will write the name here. It falls beyond the scope of what we are doing. We are not going to be doing it. The basic premise being, if I know how a dynamical system responds to a pulse or an impulse, then I know the response of the system to any arbitrary loading, which is quite powerful in my opinion. Okay? But it does not pertain to what we are doing here. Our goals are a little more down to earth. Okay? Hang on a minute. I'll complete this and then we will answer questions. So we've defined the impulse function. We've come up with some fundamental equations that help us understand the impulse function. What's the Laplace transform of the impulse function? There are millions of ways of doing this, okay? Here is the easiest way. First thing is I want to consider this very nice, beautiful property of impulse functions. Okay, it's called as the sampling or sifting This is the property that I'm going to use. You will see how this is very useful. Take any function, some f of t. Okay, consider some function f of t. Multiply this with the impulse function. It is completely fine for me to say that this product can be written as the following. Does this make sense? Why does it make sense? If at all it does. Yes?
T only has a value of 0.
Delta of t, fantastic, has only a value at 0. So any other value of delta of t at time t greater than or less than 0, the entire thing is 0. So this is perfectly fine to write. Okay? This is because delta of t is 0 everywhere, but at t is equal to 0. Okay, this is the reason why we can write it. And now see, if I consider the integral minus infinity to infinity f of t delta of t dt, if I consider this as an integral, I can rewrite this as integral minus infinity to infinity f of 0 delta of t dt. F of 0 is no longer a function of time, I can take it out of the integral. What is the integral of delta of t from minus infinity to plus infinity? It's equal to 1. So this is just f of 0. So very curious function, right? It's in reality, physically speaking, not a function because it's not a continuous function for sure. It also does not satisfy certain requirements of an actual function, but for the sake of being an engineer, we'll call it as a function. Okay? It has the following properties. It has a magnitude that is infinitely large when t is equal to 0. And more curiously speaking, its area is equal to 1 between minus infinity and plus infinity. And so this property is called as the sifting property or the sampling property of delta of t. What do you do when you sift? You're searching, right? You're rummaging through things. So what delta of t is doing is it is rummaging through all of f of t and then finding out, hey, f of 0 come out. That's why it's called as a sifting property or a sampling property. It samples all of f of t's values and says, okay, f of 0 is the sweetest, takes it out. Quite beautiful. Yeah? So we're going to make use of this property to obtain the Laplace transform. I'm going to continue here. So how to take the Laplace transform? By definition. Laplace of delta of t. I will use the proper definition of the Laplace transform. This is 0 minus, you remember our lower limit was 0 minus for all typical Laplace transform definitions. Delta of t e to the power minus st dt. I can rewrite this by using the sifting or the sampling property, that this is 0 minus to infinity e to the power minus s times 0 delta of t dt. What is e to the power minus 0? is 1. So this is essentially 0 minus to infinity delta of t dt. What is that integral equal to? It has to be equal to 1. 0 minus means I'm starting slightly before time t is equal to 0. So which means I'm including all kinds of things happening after and at time t is equal to 0. So obviously this is equal to 1. And so you see Laplace of the impulse function is 1. Okay, this is just equal to 1. And this is a curious function, but it's also a nice function because it doesn't make you do too many things. Laplace of delta of t is 1. I don't need to do too much of partial fractions and so on. Okay, it does not add an extra term to the denominator for me. Does this make sense to everybody? Okay, this question. Oh, you can write it as delta of 0 as well. Does not matter really. Because its value is defined only at t is equal to 0. Mathematically speaking, we don't put a value of t is equal to 0 here because it is understood that if you're talking about delta of t, it's defined only at t is equal to 0. Okay, the question asked was, okay, why am I putting 0 only here? Why am I not putting 0 here? Fantastic question. Because it is not necessary, because based on the definition of delta of t, it's defined only at t is equal to 0. Okay? Alright. So I'm going to bring this board down and then we're going to look at the impulse response of first order systems, keeping this in mind, keeping delta of t is equal to 1 in mind. Okay? I'm going to wait and see if there are any. Hey, you had a question? Yes.
So, like, for the convolution integral approach, I'm just asking for
Maybe it's a longer conversation. We could have it after class because it does not pertain to the scope of this class. Yeah? Thank you. There is a course called ME 5240, which is Introduction to Vibrations. They talk about the convolution integral there. If you take intermediate dynamics, we talk about the convolution integral there. So there are courses that talk more about it. It's not under the purview of 3260, okay? Even though it's a very powerful technique. We have other things to do. But we can talk about it later. Okay, so impulse response of first order systems. Of first order systems. To do this, I'm going to recall the impulse function, the photograph or the figure that you want to keep in mind. This creature is called the unit impulse function. Once again, this 1 is not the magnitude of this delta of t. The magnitude of delta of t at t is equal to 0 is infinite. The 1 represents the area. I can, on the other hand, have something called as a scaled impulse function. Multiplied by a constant a, which means that essentially its area is no longer 1, but its area is equal to capital A. Okay? So this is a scaled impulse function. This is a times delta of t. This is at t is equal to 0. A scaled impulse. Okay? And the practical application is in many situations you have a hammer blow or some kind of an impact. That impact has a certain magnitude, the force is a certain magnitude. So this A becomes the magnitude of that particular force, the area under the curve at that instant in time, okay, over a very short duration of time. So using this, not the magnitude, the area under the curve, sorry. we want to achieve the following. I have a first order system. Now x dot plus x is equal to a times delta of t. I want to obtain the response of the system. Okay, and let's say initial conditions, x of 0 is equal to x naught, obtain response x of t. And this is a response to an impulse input, so this is called as an impulse response. Response to a step function is called as a step response. Response to a ramp function is a ramp response. Response to a harmonic function, which is what we are heading towards by performing frequency analysis as the semester winds down, that will be called as harmonic analysis or harmonic response. What's a harmonic function? Is a sinusoidal function. Okay, so here, Laplace on both sides. This is a linear system, right? I've seen countless people trying to apply Laplace transforms to nonlinear systems. Cannot happen. Laplace is only for linear systems. Okay, Laplace is a linear mapping. Okay, so you can apply it only for linear systems. So if I look at this one, this is tau s times x of s, x of 0 plus x of s. Right hand side is really nice. Laplace of the impulse function is 1, so it is just equal to a. This is because Laplace of delta of t is equal to 1. Rearrange the terms. Tau s plus 1 x of s is a plus tau times x naught. All right, now I take the characteristic polynomial. We've done this multiple times. The tau s plus 1 is a characteristic polynomial. For a positive value of tau, the system is stable. Okay, so I'm not going to rewrite that again. So x of s is a. I'm going to take the tau outside the characteristic polynomial, so this becomes. I'm taking tau as a common factor, sticking it to this character capital A because I can do that. And x naught by s plus 1 by tau. The tau that accompanies x naught cancels off with the tau that I take as a common factor. We've done this for this unit and the step and the ramp responses. This is it. Do I need to do partial fractions here? I don't need to do partial fractions at all because I know that the top is a constant, which means that the inverse Laplace of this guy is e to the power minus t by tau, multiplied by whatever that is. Inverse Laplace of this is x naught times e to the power minus t by tau, the free response. This is the impulse response or x forced. This is x free. And so if I take the inverse Laplace, x of t is a by tau e to the power minus t by tau plus x naught one could plot it. T x of t. Very interestingly, the effect of this impulse response is to magnify the initial condition. Because when t is equal to 0, you see what is my value? It is not just x naught, it is x naught plus a divided by tau. So it ramps it up And of course, this is what is it going to do at steady state? This is just going to decay and go back to 0. So I ramp up on top of the initial conditions, depending on whether this is positive or negative, of course, or I could scale it down. So it scales the entire system. This value here is for x not greater than 0. You could have many combinations of this. So it looks suspiciously like a free response. And here is a common question that people might ask. They might plot this figure here, and they will tell you that this value starting here is this plus that. It looks like a free response, but it's actually an impulse response. Because the giveaway here is that I have something added to the impulse response or subtracted from the impulse response. Okay? Does this make sense to everybody? Yes, question. Yes.
So, in the impulse problem, there is no steady state.
There is no steady state in a purely impulse setting, right? So typically you can think of, you have a beam and you have a weight dropping on the beam. The drop of the weight is an impact on the beam. The beam is going to vibrate for some time and then it's going to stop vibrating. So that's similar to what the system is doing. Of course, here you don't see the vibrations, you don't see the oscillations. This is an extremely sluggish, damp system, if you think of it that way. So you can think of the impulse as just an addition to the initial conditions. So if the system were at rest, then the only thing that would be is A by tau. X naught is 0. Okay? Just an addition. Any other questions on the response types that we've done? We've done 3 types, all of them fundamental types. Okay, I have the unit step function, the unit ramp function, the unit impulse function. We've done the response types for all the 3 of them. And for Monday, to prepare us for Monday, I'm going to do one short derivation. Okay? And that is the Laplace of a time-shifted function. So Laplace of f of t is f of s by definition, 0 minus to infinity, e to the power minus st dt. Okay? The question that we want to answer is, okay, in many situations, I will start the clock, I will wait for some time, and when the system is not seeing, I will come and give it a good kick. Which means that my forcing function is actually not starting at 0, but it's starting a little after 0. Okay? So such forcing functions are called as time-delayed forcing functions. I don't apply it directly, but I apply it a little later. Yes, question?
Why would you ever just, this is like our equations we're setting up. If you kick it later, why not just say you're kicking it at 0 then? Why would you ever need to have a delay?
Because physical systems could have a delay, right? You switch on the switch for a generator. The generator is not going to immediately start. It's going to have a certain amount of inertia into it, inbuilt into it, so that the start takes place only a little bit later, you see. So physical systems exhibit delays. If you go to electrical circuits, you could have delayed switching of the circuits. You could have delayed voltage signals, delayed time signals as well. The current does not start, but then once everything is well oiled, the current starts, you see. So this is where we are heading to it. We are heading to electrical systems, essentially, by using these things. So I could have time-delayed functions. The idea is, okay, what is the Laplace of a function? I think I shouldn't say tau because that's our time constant. I shouldn't say t naught either. Capital T. Okay, what is the Laplace of capital T? Laplace of this function. Okay. With your permission, I'm going to erase this portion of the board. Did everybody get this side here? Okay. Yes, this question.
Why is it t minus capital T?
Oh yeah, why not t plus capital T? Yeah, why not, right? So here is the reason. I was waiting for the question. Okay, so this is t is equal to 0, t is equal to t is equal to minus t. If I have a function f of t and it starts at 0, this could be that particular function. Okay. If I say that a function is starting at time t is equal to capital T, all I'm doing is I'm taking this function and I'm shifting its starting point to t is equal to capital T. You see, this is, which tells me that only when the time t is equal to capital T, this function is starting. It has its initial value right there. If I start at minus t, then I would say this is t plus t. Why is it t plus t? Is because when t is equal to minus t, the function starts and it has its initial value f of 0 at that particular time. Okay? So the starting point of a function is defined by its initial value. Initial value of f of t is at t is equal to 0. Initial value of f of t minus t is at t is equal to plus capital T. Initial value of f of t plus t is equal to minus capital of t. Makes sense, right? Okay. All right. So I'm going to clear off this piece here. Keep the box. So let's start off with Laplace of f of t minus t. It's very quick and nifty, as you'll see. My definition okay, this is my definition. I'm going to do a change of variables. I'm going to say let t minus t is equal to u. Okay? So that when I look at it, if I then do the substitution, dt is equal to du. Okay? And if I do the substitution in here, wherever I have a little t, I'm just going to substitute it as u plus t. Okay, so this is now Laplace of t minus t becomes, I'm going to clear this.